example job scripts. So in this section, we discuss the running of a serial Python script using a couple of services as an example. But first let's discuss partitions because they are very important on Dardel and have some prominence on other systems. So here we have, let's start out with tetralead. If you're using tetralead, there's no such things as partitions. If you move on to Dardel, there's quite a few partitions, and so the key partitions are named shared, main, long, memory, GPU, and GPU-GH for Grace Hopper. So these first four types are CPU nodes, and there are differences with respect to job limits and things and memory you can request. So for lightweight work, you want to use into shared nodes. Here, the node type is thin, so it doesn't have so much memory installed, but here you can get a part of a node. So a single core, you can have 16 cores. What you have to keep in mind is that Dardel has very beefy cores of very beefy nodes of 128 cores. And so if you use the Dardel node for 10 hours, that's 1,200 core hours gone. So if you cannot reasonably use this 128 cores, I think you should be looking into the shared partition. There you can get part of a node and you can run for up to 7 days. Then if you have a setup which can use 128 cores simultaneously, you might want to look into the main partition. Here you get exclusive access. That means all the resources of the node, all the memory, all the bandwidth, network access, all the memory bandwidth, and all the cores of the nodes are yours. And you get charged for all the 128 cores. So you have really to think of something what to do with all these cores. This is quite short running. Here you can run up to 24 hours, which in many cases for parallel jobs with 128 cores, you can get a lot of work done in 24 hours. There's the long partition. Here only you get thin nodes, whereas in the main partition you also get nodes with larger memory. And here you can run up to 7 days. And then there's the so-called memory partition, where you can have large, huge, and giant nodes. And again, this is exclusive, and you have 7 days. There's also differences with respect to how many nodes there are. So for instance, in the memory, the giant nodes, there are not so many. So if you request such a node, you have to be prepared to spend a lot of time. So in your own interest and in the interest of everybody else, if you don't need this very large amount of memory, don't go there. Don't request them, because if you request a different node, most likely you get turned around easier and leave the nodes with a lot of memory to those which really need it. Then we have GPUs. The GPU partition is with AMD GPU, and recently we got a partition GPU Grace Hopper, which has NVIDIA Grace Hoppers. The GPU nodes are 24 hours and exclusive access. On Cosmos, there is some use of partitions in order to switch to GPU nodes. If that interests you, please visit the LUNARC documentation here, and if you struggle, drop us a support request. And Kebne Kaiser, everything is in a single partition.
Would it be possible to zoom in on the lecture a bit?
Please.
On the slides? Would it be possible to zoom in on the browser?
Yeah, Benta. Happier? Happy?
So now you're sharing your full screen, so maybe
I made the font larger. Is that?
Yeah, so let's ask our participants if that is better or not. For me, it's okay, but
It is really
easy
hard
always.
to follow on the small screen. Please either share only your browser or make it bigger.
So I made it bigger quite a bit, but it has its own. Okay, stop share. Share. So let's see what we now can get. Command minus. So how's that? If you don't say something, I can't.
Better.
It's perfect. Nice.
Cool. Nice, yeah. So I said that if you go to the explanations, exclusive nodes, that is all resources are yours and you have to pay it for this 128 cores. With part of a node, you can request up to 128 cores, and then by using the minus little n and the minus c also adjust how many cores you actually have. So that is what you want to use for serial jobs or small parallel jobs. So for instance, in that context, a 32-core parallel job is a small parallel job. So here we have, the next thing we have is a serial script. Let's start with tetralit here. First, we have a shebang that ensures that you have a bash script, bash shell. If where you start the thing is a different shell, that will switch to a bash shell, making sure that everything down here is interpreted in the way you want. You give your account, your project ID, that Slurm knows where to charge that run. Then you specify the time. We discussed that. It should be a bit generous, but not excessively generous. And then we have here one core. Actually, I'm not sure how tetralit is set up. It might be super. It might be not needed. We have to look that up and modify the scripts. That applies for all the machines. We have it here. We should have checked before the course. We didn't get round. Apologies for that. So it doesn't harm. It doesn't harm if you put in a statement sbudge minus n1, which asks for one core. Here we have the output. So I called it here process. You can call it whatever you want. You can call it Charlie Brown, or you can call it Snoopy, or in general, I would advise call it something which means something to you, metadata, something which is descriptive for the run you're doing. And then very important, the %J, it puts the job number and prevents the output. Cut $0, it puts the Slurm script into the job output. So the Slurm script goes in here, so that you can always check what did I specify in the script. If something is not as it should be, you can check, for instance, whether you made a mistake here or further down. Then it's recommended to load the modules. So we discussed it this morning. You can load the build environment for GCC, and then we have you can load the Python. So not using this system Python, but a special Python. And then you have to know that NumPy on tetralit sits in this package SciPy bundle. So this is a Python without the NumPy. And if you want the NumPy, you have to load these things. And if you load these three packages, they load a lot of stuff and make things work. And then you can run here your Python script. Let's go for Dardel. A lot of the comments I said before and are the same. You have a project, a time, asking one core. Here, very important, the shared partition, that I get a single core and not have to pay 128 cores for one core of doing some work and 127 cores watching. We have the output files. We have this. We have the cut $0, putting this Slurm script into the output. And then here, the recommendation, unless you have special needs, is to use the Cray Python, which is 3.11.7. There's a NumPy included, so no special loading for the NumPy, and then you can run your script. We have here Kebne Kaiser. here is actually an account specified. Please replace that with your own account, otherwise it will not work. The time minus N1. This example here lacks the cut $0, so I would recommend to use that. And here you load a GCC, which was used to build that Python, and then you load the SciPy bundle, which makes a NumPy available. And then you can run your Python script. Cosmos is very much a similar story, and Pele is also not very clear. On Alvis, you should not run serial jobs, since this is for GPU only. OpenMP and shared memory programming. Shared memory programming is a parallel programming model associated with threads. You start a Unix or Linux process which spawns threads. The memory of the process can be accessed by all the threads, and the threads are typically placed on and often bound to a different logical or physical core of a single hardware node. And that's very important. If you want to run threads, you cannot run on cores located on different nodes. Everything has to be in that single node you're running on. So the number of cores is limited by the hardware. So on Tetralead, where the core nodes have 32 cores, you cannot run shared memory processes with more than 32 threads. I said that already. Okay. There are a couple of APIs which you can use for shared memory programming. OpenMP is a widely used API in scientific computing to facilitate shared memory programming, in particular in a C and Fortran context. The behavior of an application using OpenMP can be controlled by a number of environment variables. So typically, you can code that from inside the application, but that is most of the time not done. It is controlled by environment variable. And even the behavior of many applications using a different APIs in OpenMP to facilitate shared memory programming can be controlled by OpenMP environment variables. So OpenMP had such large impact that many applications listen to OpenMP environment variables, for instance, to call the amount of threads to be spawned. So when executing shared memory applications, unless there is a suitable default, one needs to ensure that only one task is used. This can be done by using the -n option of Slurm, for example, having a line sbatch -n1 in the script. The number of cores to host the threads can then be requested by either using -c or --CPUs per task option, both of which do exactly the same thing, so one use only one of those. The following would request 8 logical cores. So a very important thing is, I come back to this issue of logical cores. Depending on how the service you are using is configured, you might be requesting logical cores with multiple logical cores being placed on a single physical core. This is called hyper-threading or simultaneous multi-threading. It's important to experiment whether placing threads on multiple logical cores of a physical core benefits or hinders the performance of your application. So what does that mean? Sort of modern x86 processors have something which is called hyper-threading. So the hardware supports that 2 computational threads get placed on a single core, and it takes a few instructions of one thread, few instructions of the next thread, and runs that through, and at the exit it sorts it out. So it then depends what your application does. if the both threads are doing essentially the same thing, typically there is no performance benefit from that. And actually, it might be that the simultaneous multi-threading hinders the performance of your application, in which case you should not use that. If the both threads are doing very different things, you actually might get a performance benefit out of simultaneous multi-threading or hyper-threading. So if one thread hammers the integer unit while the other thread hammers the floating point unit, then you might actually see some benefit. Most or many applications in scientific high-performance computing are using a programming model where both threads or all threads do essentially the same. Typically, for these type of applications, there's limited benefit. That is why many services have switched that thing off at boot time, and you can't engage that. So it very much depends. Okay, tetralid. Hyperthreading is not active on tetralid for the reasons I outlined. By default, a single thread is placed on each core. In the following, we give an example using thread binding, which typically benefits performance. So I have seen machines in the past where you got a 1.5 times performance benefit out of using thread binding. Typically these days it's more a few percent, but it makes stuff more cleanly. When using binding, one can easily modify how the threads are mapped onto the hardware. This can be done by changing the value of the environment variable OMP process bind. It's advisable to experiment with the values close and spread for the binding. This can be accomplished in the below script by commenting the unwanted option out. And what is behind here, close is typically advantageous if the performance of your application is limited by how fast the threads can communicate. On the other hand, if all the threads are just asking data from main memory like tomorrow, you might experience better performance by using a spread binding. If you don't know that beforehand, just do a run with close, do a run with spread, and what is faster wins. Okay, so here we have a sample script for tetralid. Okay, it is just my comments are too long. So this is very much what we discussed here. Ask for 8 cores here and modify for your needs. Very important, due to hardware restrictions, there's only 32 cores on tetralid. You can raise that value up to 32. So here we have an example of 8. We discussed that. We have our cut $0. Here we have the 2 choices. So this is commented. This doesn't play right now. And here export OMP process bind equals close. For that to work, it's very important that you're on bash shells. So for instance, C shells, that syntax fails. So be sure you have this line up here. So this is now bound to close. And then we engage process binding. We say every thread should be bound to a physical core, and we run our application. We start that like we would start a serial program. Then you might want to experiment whether just uncomment this one and comment that one and have a second run of the same thing and see whether either of them is faster. Other thing which are worthwhile to experiment is whether here we have asked for 8 cores, but is 8 core a good number? I don't know, you don't know, nobody knows until you try. So it might be worthwhile to put the same thing in with a C value of 4 and a C value of 16 and see, does it get faster if I put more cores? Does it get faster enough to make it worthwhile, the increased cost of the run? Or should I go actually lower because the parallelization doesn't work so well and I can save some time? So if it's not faster at 8 than it is at 4, you are just blowing your allocation by not achieving anything if you were not to change that to 4. Okay, let's see on Dardel. We have here examples for Dardels. And Dardel is actually a bit tricky in that regard. So on Dardel, hyperthreading is engaged. And the use of the shared partition is typically recommended to run application spawning threads, such as those parallelized by OpenMP, unless you can really make sense out of 128 cores. And the problem now is that different compilers react differently to hyperthreading, in particular in combination with thread binding. So how Slurm is set up, by using the C option of SBudge, you request the number of logical cores for your run. There are 2 logical cores per physical core. So hyperthreading is on, and that presents itself to the operating system as 2 logical cores, and that is called the hyperthreading. If you comment that line, sorry, I don't understand this right now. Let's see. Let's see whether it becomes clearer. We start this with a submission script for the Cray Clang compiler. It is what this morning I told as commonly referred to as the Cray compiler. It's advisable to experiment with close and spread binding, and as well as with binding to cores or threads. Binding to cores will not utilize hyperthreading, while binding to threads does. Each of the 2 options we have provided For each of the 2 options, we have provided the relevant lines in the script. Comment or uncomment to explore which gives best performance for your application. So here we have an example. We have discussed that, and with -C8, you request 8 logical cores. Depending on whether you now have hyperthreading on or off, you can run 16 threads or 8 threads on the node. We have here 5 minutes time. We discuss that. You load the Cray programming experiment, Cray programming environment. Here we set the binding to close. That is advantageous if threads communicate a lot. If they mostly pull data from memory, comment this one and uncomment that one. And then here, if you export OMP places equals cores, this whole thing will spawn 8 threads, 1 on each core. If you comment this line and uncomment that line, it will spawn 16 threads, 2 on each core. And then you run your application and see what wins. So there's a lot of experimenting which you can do, and if you run similar jobs quite often, it is often worthwhile to do that in the beginning, to run a number of experiments to get an idea: is 8 cores a good number? Should I use hyperthreading? Should I not use hyperthreading? Should I bind close? Should I bind spread? I hope you get that. On the other hand, if your application has been compiled using GCC 13.2, the following script should work. Again, one should explore the effect of close or spread binding. If you want to engage hyperthreading, uncomment the line setting the OMP num threads environment variable. So let's see how does the script look. This looks very much like before. Nothing has changed. We load a GCC compiler. We have our binding, spread or close, and we always bind to cores. So and then comes the magic. So if I don't set OMP num threads, it will now run with 16 threads, 2 bound to each core. If I only want not to use hyperthreading, the recommendation is that you uncomment this line. This Slurm CPUs per task are set from this number here. And we divide that with 2, such that only 4 threads are spawned, and the application runs with 4 threads on the physical cores. So here you can experiment a lot what gives you best performance. So it is close, spread binding, hyperthreading on, hyperthreading off, and what is a good number over here. Okay, so much on OpenMP. The next section is about running MPI applications. So message parsing is so this is very different. Message parsing and distributed memory is sort of two names for the same thing. You have your memory is distributed over a number of tasks, and then you use message parsing to facilitate the communication between that. In the area of scientific high-performance computing, the message parsing interface MPI is the most commonly used API for to achieve this. So here down, I have an illustration what message parsing is. We have done 5 tasks numbered from 0 to 4, which means that I run 5 copies of my program, or actually I can use 5 different programs. So in this example here, I just run 5 copies of the same program. So that is very important if you program message parsing, or if you use also to some extent, if you use message parsing application, that you understand if you run this message parsing on 10 cores, you run 10 copies of your program. You run 10 typical programs. If you run on 5 tasks, as is shown here, you run 5 programs, one on each core. And between these programs, you use message parsing to copy data from one task to the other one. What I have shown here, the execution time runs from top to bottom. And so yeah, this is something which is done quite customary. So with an MPI program, or you need to get some input data, and good practice is that one task here, this task number 0, reads the input file. So for instance, something like simulation temperature, simulation pressure, how many particles are in that simulation, all this type of things. Task 0 reads that and then just copies the value to the other tasks. That is shown here. And then the thing's running, and quite often you might split up the simulation volume, that each task gets a sub-volume, and then the tasks need to exchange the border values, which is shown here. So the tasks, they calculate for a short while, they exchange data, then they calculate again, exchange data, calculate, exchange data, and so on until that is finished. So ideally, with this type of a setup, when running on 5 tasks, I would get speed up of a factor of 5. So only 20, the run would take 20% of the time it would have taken if I were to run on 1 task. So very important, I mentioned that to understand is you run multiple executables when running an MPI task, and you typically start one executable on each requested course. Most of the time, multiple copies of the same executable are used, but there are exceptions for that. So what you need when running MPI program, you need another program which is called the job launcher. And what that does, it takes your executable or the set of executables and gets that started on each core which you have been allocated by Slurm. And depending on the system and the libraries used, the name of the job launcher differences. So down here we have example for NAISS Tetralit and Dardel service. To run a parallel job. So going in here, So on Tetralead, the recommendation is to, if you want to run with 16 cores, to run -N16, and the setup at NSC is modified to ensure that the 16 cores are placed on a single node. So here we have half a node, the other 16 cores of the nodes will go to other users. Then here's nothing changed, and then down here we have run your MPI executables. Here we have this thing, this MPP run is the job launcher I referred to beforehand. That is a program. Here you have your executable. It's compiled from Fortran 90. It takes the executable and runs 16 copies of that, one on each core. And here you have an input value of 10,000. And here is, okay, there's not so much interesting here. Let's, where is my Dardel script? Here is the Dardel script. So here we have an example of 2 full nodes with the Clang compiler. So it's 256 cores. So with 256 core, even modest runtimes will be expensive by means of CPU hours for your allocation. So if you have 256 cores, you run for 4 hours, that is 1000 core hours of your allocation done. So you better use that, you use all of them in a decent fashion. So scripts requesting multiple nodes are required by projects which have been allocated significant resource allocations and need to run large calculations to achieve their project goals. So this is something where if you got a large allocation, so typically these are the projects which can make good use of a large number of cores in a single run to get a lot of computational work done. So what we have done here, this is what we had before. The interesting bit is over here. We asked for 2 nodes, and then we use n tasks per node equals 128. That is a good way to achieve that your 256 cores will be placed on 2 nodes, and then you get 256. That there has been some discussion around if you just ask for 256, they might be splattered over the whole machine, and you lose a lot of time in network communication and are exposed to what other people are doing on their nodes. So here, that is typically the preferred choice, that you ask for full nodes and calculate the number of nodes. The logic of that will work on any service. It ensures that you get allocated full nodes. This is stuff which we had before. Then here we load for the Cray programming environment, perhaps load the PDC 2411 module, which makes the PDC module available, but the Cray programming environment with the Cray compiler is the default, so nothing else needs to be done. And then you run your MPI program. Please note that here on Dardel, srun is recommended as the job launcher. That is the program which takes this executable and places 1 copy of this executable MPI hello on each of the 256 cores that is distributed over multiple nodes. Yeah, sorry, I got stuck. I was wrong-footed. So here we have now an example if you want to use a partial node. So let's, I went over that too quickly. Since here we have requested 2 nodes with 128 cores, we have been asked to place on the Dardel's main partitions where you get full nodes allocated. Now we have an example for a program which is not capable of making decent use of 128 cores. However, it runs well on 16 cores. So here we have now asked to be placed on the shared partition where we get only a fraction of the node. We ask for to be placed all our cores on one node, and we have 16 tasks on that node. That leaves 128 minus 16. That is 112. I think 112 cores, that means 112 cores for other users. The rest is very much the same. So this example is again for the Cray compiler. If you use, or the person who compiles the program for you, use a different compiler, you are recommended to load the module for that different compiler. And here then, this is an example for the integration 2D. Again, we use srun for the job launcher, and then it takes the executable and it takes the argument and passes that to the runs. So here now srun, it will listen to here, and now it has now figured, this time it's only 16 cores, and it will start 16 copies of your program. Instead of ups here, we had 256 copies, and it listens to that as well and starts 256 copies. So this is quite clever. So if you have standard examples, the recommendation is not to put any core count here, because srun will listen to that. So here I said that we ask for whole nodes and possibly tasks per node. srun and MPI run should be interchangeable at many centers. Tetralead uses MPP run and Dardel srun. Remember, you need to load modules with MPI. So the MPI module needs to be loaded, which applies to all the machines instead, with the exception of Dardel, where it is built into the executable. At some similar to OpenMP, at some centers, core binding is recommended if you run standard. MPI jobs. Core binding gets a bit tricky when you combine MPI with OpenMP. It's very easy to shoot oneself in the foot with core binding, and so then you need to do special things. But for standard MPI jobs, it's typically recommended. So then we come to memory-intensive jobs, and that is something which, is one of our specialty in the support system. Users run into out-of-memory errors running OOM. What that is, so if you run out of memory, so you request memory, we show you that in a minute. But since nodes don't like if more memory is used than they actually physically have, they would get very slow, and in high-performance computing, that is typically not like. So if your program consumes more memory than you requested from us or got given from us by default, the program is terminated. That is how the systems are configured, and that is to protect the users which are running on the same node as you, which have requested the correct amount of memory and are expecting that the node is performing well, that they can get the work done. So if it typically says OOM kill in the job output, so check the Slurm errors and log files what the issue is. Typically, if you know what it is, OOM, out of memory kill, then you know what it is. You can also check with these tools, depending on the cluster, what the issues are. Fixes are used, there are a couple of fixes. So one thing is some services have fat nodes, nodes which have more memory installed, where your fair share of memory is larger. You can allocate more cores just for the memory. Or you can start modifying your app or tweaking your app if that's possible that it uses less memory. So one way to increase memory per task, it's worked generally and it's typically quite simple, is just to pretend you are using threads, but actually not. So here we have a simple example. When using 16 tasks for an MPI program, but that MPI program is not happy with the amount of memory it gets by requesting 16 tasks, you tell MPI, you tell the program, we are also using 2 cores per task. That means you're asking for 32 cores in total, and you can do that as described here. The caveat is here, you're running 16 tasks, and you are using 32 cores, and we will be charging you for 32 cores. That's just how the cookie crumbles. If you take the memory for each task, you take the memory of 2 cores. We can't give the cores without memory to another user, and you just have to pay that memory. In principle, there's nothing so much if that is done consciously, because the program would fail. If you just run without this CPU per task equals 2, there's nothing bad about that, because in the end, it is your judgment. You need to get your science done, and for that, you need to get the machine to calculate. So here we have a simple MPI job, a sketch of an MPI job asking for 8 cores with 2 cores per task, and to start it with you start it with srun. Then here we have an examples template for a serial job where you just put c equals 2, and then you load twice the memory. At some centers, you can also use sbudge memory per CPU. You can explicitly request how much memory it is. Here comes a number, which is the memory in megabyte per task. Again, if you increase that number, you will be leaving cores without memory, and your account will be charged for these cores. So here we have for a couple of services, if you want to get placed on fat nodes. So on Tetralead, the standard partition has 96 gigabytes, which on 32 core nodes, which makes 3 gigabytes per core. And if you want all the node to yourself, you can put a -c sin, ensuring that you are placed on a sin node, and exclusive flag, you get all the cores for yourself. If you want fat nodes, they have 384 gigabytes per node, which is 4 times the memory. You can do a -c fat, and again, if you want the node all to yourself, you can put the exclusive flag. So here, by adding these options to your Slurm script, you will be placed on the fat node, but there are so many more sin nodes than fat nodes. You will wait a lot longer time if you request fat nodes than the sin nodes, so only use that if you want. On Dardel, we discussed that before. We have partitions. So there are sin nodes, which have 256 gigabytes. That's 2 gigabytes per core. We have twice the memory, 4 times the memory, and giant nodes, which have 8 times the memory. All these partitions here have 228 cores. And depending on the partition you're using, you have access to each node. So in the shared partition and in the long partition, you only get the thin nodes. If you go for the main partition or memory, you can have access to the large and huge nodes, and the giant nodes you have to go for the memory partition. And if you want to be placed on these nodes, so let's say you are in the main partition. In the main partition, you have a choice of the first 3 of the nodes. If you do nothing, you most likely get placed on a thin node. If you want to make sure that you at least get a large node, you have to put minus mem equals 440 GB. If you want a huge node, you have to put Z. You can't put Z unless you're in the memory partition. If you go for the memory partition, you have access to these 3 partitions, and by putting the relevant requesting flag, you can get control which of these kinds of node you get. Please take in mind there are very few giant nodes, so waiting time will be very long. Here we also have the GPU partition of with the AMD GPUs. For that, that has fewer cores, therefore it has 8 GB per node, and you have to do a mem 440 GB to be placed there. So a few comments on Pele. The compute nodes CPUs have SMT enabled as simultaneous multi-threading, also called hyper-threading. So that is similar to Dardel. And there each core runs 2 threads, and in Slurm the threads are referred to as CPUs. So with -C you request 1 hyper-thread. If you don't like SMT, you can add the option --threads per core equals 1 in your job script. And here's a link on simultaneous multi-threading in Pele. And with that, I think I give myself a break, and I think I hand you over to Diana, who is continuing.
Yes. So I am going to take over the screen share. Let's see. So let's see, is this big enough for you?
Fine with me.
If it's too big, let me know.
I think it looks fine. It's
Okay.
fine.
So then we'll continue with IO intensive jobs. And by IO, I mean input output, reading and writing to the disk. So, I mean, dealing with jobs that do write a lot can be tricky, and specifying with the disk that you are doing this on can be very important for some of these jobs. But well, typically, anyway, what you want to do is that, well, as a first choice, you should use the project directory for the input and output of the files produced by your programs. Sometimes, I mean, some clusters, actually, most clusters within NAISS do have several. Well, one environment variable which is associated with the so-called node local scratch disks. So these are this is hardware which is local to the compute node, and that typically makes the reading and writing to files quicker. So this environment variable, sniktmp, called sniktmp for historical reasons, is usually actually the same as the tmp dir variable as well, and then it points to the /scratch local disk. This is, for example, one example on how you can use these environment variables in your script. So in addition to the usual sbatch flags, sbatch, options that you have in the script and while loading the typical modules and version that you may need. So what you want to ensure is that you copy the necessary data that you want to be on the local disk. So copy the data to this local disk defined by this environment variable, sniktmp or tmp dir. Then you go to this directory, and then you run your program. And then all the output files that will be generated by the program will, by default, unless specified differently in the program, will end up in the sniktmp directory. Now, what is important that you do is to copy back the results to the submission directory. Otherwise, they will be left on this local scratch disk. And why this is important is because these local disks are cleaned regularly. On some systems, I mean, they are cleaned up as soon as the job is finished. So it is imperative that you do have this line in your script. Now, this is how you can use these scratch disks. The question is, should you do it or not? So I would say that it's hard to say unless you are actually going to test your program. But typically, if you have a lot of local files, a lot of temporary files which are being produced during your run, then it is useful to use the scratch. If you were just to read one big file at the beginning of your program and then do the computations and then write something at the end, then it may be actually not necessary to use the scratch. So it's something that you need to try out. But typically, as I said, it is useful if you have lots of temporary files which are being written and read throughout the run of the program. Okay, so a little bit about job arrays. So this job arrays is an option that you can use to Slurm in order to submit and manage jobs which are very similar. So initially, what you do is you specify sbatch options in your job script, and the sbatch options which are specified, like the size of the job in terms of number of cores or number of nodes, the wall time, and other options that you may have, they will all be inherited by these different arrays that you submit from one job script. And as we see, well, the individual job arrays, they can have different input parameters that they are run for, and then these execution times can vary depending on what this input data for the job array is. And the sbatch option that you use in the job script is the -- array. Sorry, there should not be a space in between here. Just a word of caution that, of course, you can submit many job arrays, and the limitation is just set by the system administrators. I mean, on different clusters, and maximum number of jobs that you can submit is different. Okay, so now let's go through a simple example on how you can use job arrays, and I'll take this simple hello world array Python script. So what it does is that it simply prints a simple message for a given argument. So if I am now to incorporate this small program, this small Python script into my Slurm script. So what I have is so let's see, I have I am asking Slurm to let's see, to give me one core. So I will run this hello world array on one core for a maximum of 5 minutes on a given account. But then instead of running this only once, I actually want to run it 10 times. So then what I tell Slurm is that, okay, do an array of Slurm jobs with an index from 1 to 10, and each of these arrays should run on the resources which are being specified with as batch, and the work that should be done is well specified in the rest of the job script. So it loads first a given Python module, your preferred version, and then it runs the Python script. So there is an srun Python, a lowered array. Actually, srun is not really needed in this case because it's just one core. But in general, I mean, you want to run for several cores. Then the argument of each of these arrays is different. And in this case, the argument is just a Slurm array task ID, but it can be something different. I mean, depending on what is suitable for your program. And there are really many options that you can use with array. I mean, some of the most common ones is to specify the index for the array in different ways. So it does not necessarily have to have a step of a default step of 1. You can have different steps, and the range as well. I mean, can be specified in many different ways. What is important, I think, is to remember that you can redirect the output that Slurm produces for each of these arrays to different files. This is the default, but I mean, this can be changed. So the %J stands for the job ID, the Slurm job ID, but then each of these, the job ID is going to have a sum index, which is the index of the array. So this %A. So again, J for the Slurm ID and A for the array index. Okay. And then this dash A, sorry, not dash A, %A can be also specified as an environment variable, and it's this Slurm array task ID. So if you want to do some bash scripting using this array task ID, then it's useful to remember this environment variable. Now, a little bit about running GPU jobs. And because, I mean, the NAISS clusters have a diverse offering of GPU hardware, it's not entirely trivial to know, I mean, how which settings you should use when you want to run jobs. What I do find useful is to use this command sinfo, and we've seen some of these already. Let me just copy paste this and, for example, show it here on Tetralith. So what I get here, so let me just go back a bit and show this command without piping it through grep GPU. So what I can see is all the partitions which are defined on Tetralith. It's only one, and the default one is Tetralith. But by using this particular output option, so %G, I see the GRES the GRES configurations which are defined on the tetraleaf cluster. And in this case, it's the GPU T4. So this actually this actually indicates that these nodes, I mean, from 69 to 128 and so on, they are all equipped with GPU cards as well of Tesla T4 type. If I were to do this on Lardel as well, I would get a different information. And the same, I mean, on other clusters. So this is a universal command. You can use it on any cluster, and of course the output will be different depending on what is set on that particular cluster. So in the case of Dardel, then we have nodes which are equipped with 8 GPUs each. And actually, if we go back to the lecture notes, those are these 4 AMD MI20, 250X, which each have two GPU cards. So it's seen like as 8 GPUs. But yeah, so it's 4 times 8. And it's not indicated here, but in addition to these AMD GPUs, as Joachim mentioned, there are also the Grace hoppers, but they are limited to certain groups, and you really need to prove that you need NVIDIA GPUs in order to get access to them. So, so as it is right now, if you need to use NVIDIA GPUs, then you should use Alvis, at least until Arenus is up and running. So yeah, so Alvis is the system that has most of the current NVIDIA GPUs. So a range of Tesla T4s, A100s, and some V100s as well. But how do you actually get to allocate GPUs on different centers? Because these because the settings, I mean, for the GPU configuration is usually tailored by or has to be tailored by the system administrators. The settings do look a little bit different on the different NAISS clusters. So, for example, if you want to run a GPU job on Tetralith, then you do not actually need to specify a GPU partition. You just need, for example, to specify that you want a given number of GPUs per MPI task. In this case, it's just 1. So I have one task, 32 CPUs per task, and then 1 GPU per task. For Dardel, you do need to specify a partition, and the partition is called a GPU. Maybe different on other systems, but let me show you again. So, I mean, if you do sinfo, then you can actually see that if you don't remember, or if it's different on a different system, what the partition is, you can check that with info. On Alvis, yet again, it is it has a different name. And also, I mean, the GRES configuration is defined differently. So, so what you need to specify after GPUs per node or GPU is the type of GPU that you want. And this is important because, I mean, Alvis has many different GPUs that you may choose from depending on your needs. So what the type is, be it a V100 or a T4, needs to be specified. And then the X here is the number of GPUs that you wish to have. I will not go through other examples as we'll mostly focus on the NAISS clusters here, but you can read that on your own later. So how does the let me just show you one example of a job script for the tetralift. So again, in addition to the typical S-batch options that you have seen previously, what you need to add is information on how many GPUs you want to request. So in this case here, again, I am requesting for 1 GPU per task. And then one should, as usual, load the needed modules unless you are running some program that you installed yourself, and then run the GPU code. So for Dardel, remember that these are AMD GPUs, and you should have a code that supports heap instructions. Then again, you need to specify the partition, in this case GPU, and then where is the information on? I think something is missing. In these cases, there is no information on how many GPUs one should ask. Seems to be a little bit of a problem. Sorry for that. So let me just open an example here. Let's see. Hopefully I have a corrected script here. So I think that, yeah, by default, this should give you 1 GPU if you are asking for if you are specifying the GPU partition. Yeah, sorry for this. I'm going to check this later. It's a bit weird. Okay, and then so again, remember that this does not support CUDA instructions unless you are using the gracehoppers. Okay. We do have a set of exercises that you may try out on these different clusters, and you find them in the course repository. We'll not have time to actually go through all of those, but I do recommend that you take the ones you are mostly interested in and try them out. Some very simple examples on how you can use Slurm for other kind of jobs. And maybe not many of you who are running serial codes anymore, but sometimes that is needed simply because, well, you have some program that has not been parallelized yet. So one way to run multiple jobs, serial jobs simultaneously, so the jobs that only can run on one core, is by simply having different programs running in the background. So for example, you start this program with some input data 1 in the background, specifying 1 core only, with the exclusive option here, which simply means that only this program should run on exclusively on a core, and other processes should not be running on this particular core that program is using. Then you simply submit other programs in the background with their own different input data. And then what is important is that you use wait at the end of this script. So this simply ensures that the Slurm job is not going to finish before these background jobs are finished. If you had not used this, then wait would not have been needed, but then they would just run one after another instead of running them simultaneously. So it is important you send them in the background and run all these different programs on different cores. Now, you may run several jobs, not necessarily serial. They can be parallel jobs. For example, these jobs are running on all of them are running on 14 cores. So again, I mean, you may specify that okay, you have different MPI programs, and it can actually also be OpenMP. Although in this case, sorry, it's MPI as we are using SRAM. So you have different MPI programs, each running on 14 ranks each. And in total, we are asking Slurm to give us 14 times 3, 56 number of cores. Again, all these programs are running in the background. So Slurm is going to end the job when all of these are finished. If one wants to add, to run the jobs not in parallel but actually sequential, then you drop this tilde at the end. So in this case, for example, multiple sequential jobs, what I do is first I run this my program data on 14 cores. When this is finished, then I'm going to run another program using 4 MPI ranks and 4 CPUs per task. And then once that's finished, I mean, I can continue with running the jobs or the programs in this script. And in this case, because these are run sequentially and not in the background, I'm not sending them in the background, I actually do not need this wait command. So this has been a little bit